All right. Good morning, everyone. Can you just confirm, am I audible? Okay. Can you see the screen? The slides are changing, right? Okay. All right. So we will start our discussion for today. And the last class we discussed about Gaussian process regression. So in today's class, we are going to extend our discussion on Gaussian process regression. So there are certain features or factors we would like to discuss. Okay. So mostly today's class will be based on that how Gaussian processes can be utilized in hyperparameter tuning as well. Okay. So we have explored different ways for hyperparameter tuning. So in the previous classes, we have seen that how random search can be utilized for hyperparameter tuning, how grid search can be utilized for hyperparameter tuning. So we have not gone through into the philosophy of all these hyperparameter search. So in today's class, we are going to discuss that how hyperparameter search can be visualized and how Bayesian optimization or Gaussian processes can be utilized while performing hyperparameter tuning. Okay, so that would be the essence of today's class. In the last class, we also uh, only discussed about the theoretical part of Gaussian process regression. So in today's class, we are going to see the implementation of GPR in Colab as well. Okay. So this will be in a nutshell today's class. So with today's class, we will be almost covering. So we have covered three different algorithms in machine learning. So I have chronologically moved from linear regression to support vector machine and then finally to Gaussian process regression. The idea was that to demonstrate that how kernel-based regressions are different than a linear regression, the simplest possible regression approach. Okay. So in today's class, we are going to complete our session on machine learning primer. The reason being that the idea was to introduce that what are the different steps of machine learning, how you handle the data, how you distribute the data in training, testing, and validation. Okay, how do you implement different algorithms? How do you export the algorithms from scikit-learn library? All those things we have discussed in last few classes. Okay. So in today's class, we are going to complete our session on Gaussian process regression. Let's start our class. So as always, if there is any query related to session, you can ask in between. You can unmute yourself and ask about the doubts. Okay. Or else we can have the doubt session after this class. So we have looked into grid search approach. So this approach is for hyperparameter tuning. Okay. And we have seen that how we can implement this grid search approach for the hyperparameter tuning for different machine learning models. We have seen this in particular for support vector machine. Okay. So this is a very exhaustive search to a specified subset of hyperparameters of a learning algorithm. Examines all possible combinations of specified hyperparameters. So how can we understand this? We can understand this with this image over here. Okay. So we have two different hyperparameters in this case, hyperparameter one, hyperparameter two. So what does grid search does is that if we have three different levels for variation in hyperparameter one and three different levels for variation in hyperparameter two. So at a time, the combination of two different levels will be utilized for individual hyperparameter. So if we just look at this row over here, so at this stage, the first level of first hyperparameter and first level of second hyperparameter is utilized and explored. Okay. So the next step, the second level of hyperparameter one and first level of hyperparameter two is explored. So likewise, all the possible combinations are explored by using grid search CV. Okay. So this grid search algorithm is quite efficient one, but there are certain problems with this algorithm. So what are those problems we are going to look at in the coming slides? Okay. One major aspect of this grid search is the number of combinations. Since we have two different hyperparameters over here and we have three different levels for individual hyperparameters. So the number of combinations would be 3 into 3, 9. So it is kind of 3 square. Okay, because three number of levels are there and two different hyperparameters are there. The number of levels raised to number of hyperparameters, that's many combinations can be made. Okay. So just imagine if the number of hyperparameters are increasing and at the same time the number of levels for individual hyperparameters are increasing. You can imagine the number of combinations will exponentially rise. Okay. And when that rise come into play, then you have to explore those different combinations. And by for exploring those different combinations, the computational expense also increases. Okay, so that is the major limitation of grid search, the curse of dimensionality. Possible combinations grow exponentially with the number of hyperparameters. As I explained, that if the number of hyperparameters will increase, the points for you to explore also increase and computational that will become more computationally expensive process. Hyperparameters values are determined manually. That is another limitation of grid search. Apart from that, does not explore entire hyperparameter space. Not feasible. It performs worse than other searches. Okay. So when we compare this with other searches, it performs not very well because when we are working with machine learning models or any other computational approach, our objective is always to have a trade-off between computational expense and the accuracy. Okay, so we do want to have certain level of accuracy, means high fidelity must be there, but at the same time we don't want the process to be computationally very expensive. Okay, so that is why we always prefer the options which are having less computational intensiveness into the play. Okay, one more problem with this is, let's see that in the next slide. Okay, so there are some advantages as well. So for models with the simpler hyperparameter space, like we have seen that in linear regression, we only had two different hyperparameters, right? So for such models, this grid search will work very fine and we can utilize it. It can be parallelized as well. Okay, so in a parallel, we can explore different combinations. That is also one thing, one advantage with the grid search. There are certain considerations associated with the grid search. That is, grid search is most expensive method in terms of total computational time. However, if running parallel, it is fast in terms of wall clocking. We run sometimes we run a small grid, determine where the optimum lies, and then expand the grid in that direction. So one problem with grid search, the major problem is that if we are seeing over here in this image, there are different levels involved, right? So now if these levels are categorical in nature, like the name of the kernels, if we are dealing with kernel based regression, name of the kernels would be the categorical variables, right? We want to explore different kernels, then it is okay. But if suppose the hyperparameter one is continuous in nature, okay, so we have certain levels, certain points in between these levels as well. So with the grid search, that becomes very difficult to capture these continuous variation. Okay, so that is the major limitation. And if we want to capture the points in between these levels, then we will have to have many different levels over here. So increase in number of levels will again increase the computational cost. Okay. So that is the limitation, the major limitation that is associated with the computational cost and not able to capture the complete domain while performing hyperparameter tuning using grid search. Okay. So now this problem can be solved by using Bayesian approaches. And for that, I would just like to recall this concept of Gaussian process as we have seen in the last class. As you can see that we started with the observation of at two different points in the Gaussian process, right? So based on that, one objective function was defined. This line, that is dotted line, it is an objective function, and the mean function is associated with this particular problem that is shown in the solid black line. So now, in this approach, what we have seen, based on this, the acquisition function was formed, and the maximization of acquisition function gives us the next point to explore, right? So instead of exploring all the points randomly in some certain combinations, it gives us the idea that where we need to explore. Okay, what can give us the better prediction or accurate prediction. Okay, so based on this acquisition function, we get the position where we need to explore. In the next observation, we have seen that that exploration gives us better result, and the objective function and the mean function are coinciding over here. Okay, again, it will give us some maximum acquisition function at some point, and that point will be explored, and based on that, it is further converged. Okay, so what I meant to say over here is that in grid search, we have seen that we have to explore different points, and based on exploration of those points, we will get that which point is giving us better accuracy. But instead, this approach, the Gaussian process, gives us the idea that this might be the point where you will get the better accuracy. You don't need to always explore all the points associated with the problem. Okay, and that's how the computational cost related to Gaussian process comes down. Okay, we have seen this with this example as well, right? Where the expected improvement was a acquisition function, and we have seen that how with different iterations, the different points were explored. So earlier, the uncertainty in prediction was very high, but at the iteration number 6, we have seen that only by exploring 1, 2, 3, 4, 5, 5 new points, the uncertainty has come down a lot, right? So this is the approach which can be utilized in hyperparameter tuning as well. Okay. So let's see how can we do that. So what is the algorithm or what is the philosophy behind Bayesian optimization while performing hyperparameter tuning? Okay. So in this, just look at the left-hand side, the flow diagram which is given. So this is the philosophy behind the Bayesian optimization algorithm. Okay. So we observe some data points as we have seen in the previous cases that we have some observation, prior observations. Based on that prior observations, we have some mean and we have some covariance. Okay. So covariance means how far the points can be or what uncertainty can be in the prediction if we go along with this region. Okay. So that is what the covariance is over here. So we start with certain points. Okay. So observe data points, build a surrogate model that we need to know what is the mean and what is the covariance. Based on that, we will build a surrogate model. Now, by using this surrogate model or Gaussian processes, we will further have the observation on maximized acquisition function. As we have seen, the domain where acquisition function was maximum, that gives us the idea that in that domain, we will explore for more points. That's what has been done. Sample next point. Okay. Add new point to the set of observed points. Okay. So now when we add the new point to the observed points, what we have observed? We have observed that uncertainty has come down a lot. That's how by increasing the sample points strategically. Here we are not randomly using any sample point. We are strategically finding the sample point. And that's how by introducing very low amount of sample points, the uncertainty in the prediction is coming. Okay. The same approach can be utilized in hyperparameter tuning. We will see how. Okay. Now the philosophy of this acquisition function. I just want to explain this in a little. So by using this right-hand side image. Okay. So this acquisition function, what is the role of acquisition function in Bayesian optimization? That is shown over here. And just consider this as your initial 2 points. So these 2 points or 3 points we have explored so far. Okay. I'm sorry. So there are 3 different points, x1, x2, x3. These are the functions. Okay. And we know that as these functions, what would be the probability distribution, okay, of the samples? Because we know that in the vicinity we have some exact solutions. As you can see, the black dots over here, black points over here gives the exact solution. Okay, and we can see that uncertainty is converging at these black points. So now just look at it that we have three different functions. We have the distribution along these functions, as we can see. Okay. Now, based on this, we have some mean. This black line over here, solid line, this gives us the mean. Now, if we want to have a threshold, okay, we want to have a threshold, as we have seen this mean, we will want to find out that there has to be a threshold of this mean. Okay. So based on the mean available, so whatever the functions we have, we will find the mean of that function, and that mean of the function can be described with this x plus, the new sample or the new point where we need to explore. Okay. So now this new point x plus is given by this black dot, and corresponding functional of this x plus, that is given as f of x plus. Okay. So now this becomes the threshold. Now, if we want to explore new point, so what is the idea of maximize acquisition function? Whatever the functionals or f of x plus is denoting over here, we will always go with the maximum points. So we will always look above this threshold line. Okay. So whatever the samples we have below, we will disregard those samples. We will disregard those new functions. We will not explore this domain. We will only explore the domain which is above this threshold line. So above this threshold line is this functional over here, so this region over here, and this region over here. Okay. Let's use it. So this is the region 1 and this is region 2, which is above this threshold line given. Okay. So that is the idea of maximizing acquisition function. That first, some unknown function has to be derived based on the known functions. X1 and X2 are the known functions, and based on that, x plus is derived. For x plus, we will find out what is the function of x plus. So based on the function of x plus, a threshold line has to be derived. And with the help of this threshold line, we will get to know that, okay, the next exploration point should be above this line. Okay. So we have two different regions. This is one region and this is another region where we can explore. Okay. Now, since this region over here, it is not much, and this region over here, we are having good amount of uncertainty. So this gives us the next exploration region that is given by X3. Okay, initially we only have X1 and X2. X3 is the new portion where we need to check. Okay, so by looking at the X3, that will give you the maximize acquisition function now give you the points somewhere here that we need to explore. And that is what the probability of improvement looks like. Okay, this PI over here. This is the probability of the improvement. So probability of the improvement is corresponding to those regions which is above this threshold line given over here. Okay. So it is little bit tricky. I hope you can understand what is happening. So I have given one link over here. You can always also go through this link where you will get the better understanding that how Bayesian optimization works, how different acquisition function works. So that is all given in this link. I have taken this information from this link itself. Okay. Now with this, we will have some idea that how we can utilize this Bayesian optimization algorithm for hyperparameter tuning in Colab. So Bayesian search is given in scikit optimize. So this is the module library which is available in scikit-learn. So with the scikit-learn, there is a scikit optimize library. Okay, the documentation for this library is given at this GitHub repository. Okay, and the codes and examples are given at GitHub. So you can find out the information from here. So now there are different search algorithms involved with scikit optimize. The first one is associated with Gaussian processes, that is GP minimize. Second one is associated with random forest and extra trees, forest minimize. then gradient boosting trees, GBRT minimize, and random search, that is dummy minimize. Now, the good thing about this scikit optimize or Bayesian search is that the objective function has to be defined by the user. Okay? So there is a uh, possibility of customization. Okay, so it is fully customizable, works with any algorithm and any package. The on, or if we just say minus side of this is that we have to code it. So this is the base search CV. This is the uh, wrapper associated with the scikit-learn models, which can utilize Bayesian optimization for hyperparameter tuning. Okay. So for hyperparameter tuning, there are different things involved. Let's see what are those. So this built-in module to create hyperparameter spaces with sample time. So there are three different classes. So as I told that hyperparameters can be varied in a real number sense, in an integer sense, and in a categorical sense. If you talk about number of kernels, different kernels we want to explore, so that will come into categories, right? If we have some numerical value, let's suppose we were talking about the number of points to be left out during support vector machine, the C, the parameter C that has to be have the integer values, right? Whereas the sigma in uh, Gaussian process regression that can be a real number sense. Okay, so this is how you can differentiate between the hyperparameters and give the hyperparameter search by using category, integer, or real number. So in that fashion only, the Bayesian optimization search will happen. Okay, so for real and integer samples with uniform and log unit. So distribution can be uniform or log uniform. That's what is written for reals and integers. These are the different acquisition functions that are available with scikit optimize. That is expected improvement, probability of improvement, lower confidence bound. Okay. These are the different built-in functions to explore the results. So we can plot the convergence, we can plot the evaluation, we can plot the objective. All right. So it also allows the parallel search. It requires more evaluations of a function of x needed, and but it reduces the wall clock time significantly if we use parallelization. So I would recommend that you should explore this part over also, since you are having some of you are having difficulty in hyperparameter tuning. It is taking a lot of time, right? So how you can parallelize to reduce the time that you can explore. Now with this, we will see that how the Gaussian process regression can be implemented in the Colab, and simultaneously how we can implement Bayesian search optimization for hyperparameter tuning. So whatever I am going to show you in today's class, that is something that you can implement for any kind of model. The only thing is that you should be knowing what are the different hyperparameters, what is the range of hyperparameters. So for that, what you can do, you can simply go to the scikit-learn. Okay? Just scikit-learn. If you Google it, you will find out there is a page associated with the sklearn Gaussian process. You will find out what are the different parameters, hyperparameters. As we can see here, for GPR, we have kernel, okay? We have alpha, we have optimizer, number of restarts optimizer. So these are different parameters associated with the model. And by playing with these parameters, we can somehow get the better model. Okay? So now just look at the code here. So I will be working with this kind of data. So what data is it? We have 5 different input features and 1 response. In total, there are 120 samples. Okay. So now just look at it. We are first performing the Gaussian process regression without using hyperparameter tuning. Okay. So in this, I'm going importing Gaussian process regression from scikit-learn Gaussian process. Okay. The kernels which I am going to import, that is RBF, constant kernel, Mattern, and white kernel. Again, train test split. This we know how why do we use this. Okay. From the metrics, we are importing R2 score, mean squared error. Okay. So now, after importing the dependencies, I will import the data into the Colab environment. The data is already available over here. So out of this data frame, what I will do, I will segregate X and Y and keeping 0.1 as the test size. I'm using some customizable kernel over here. So kernel would consist of, if I just want to have a look what the kernel looks like, just simply. Okay, so this is the kernel, what looks like. So it is having Mattern 3 by 2 and white kernel associated with this. Okay. So this is the kernel that we are going to use for model construction. In model construction, we are using Gaussian process regressor, kernel, number of start optimizer 10, random state 42. So this is something that you can vary because it is a hyperparameter. Okay. So now after doing this, we will use this model, the model one, for the prediction purpose. By train. So I'm using the train data first for the prediction and then test data for the prediction. So based on the prediction and actual value, we will get the metrics, that is R square value. Okay. We are getting sufficiently high for train and test both. Next, let's check the mean square error. Mean square error is also quite low for both the cases. You can have the scatter plot like this. You can also have the error plot. I have not done that, but you should do it whenever you are working. Now let's talk about the part where hyperparameter tuning can be performed. Okay. So for that, as I told you, that we will be using scikit optimize. For this, we have to install scikit optimize. Okay. Next, from scikit optimize, we are importing base search CV. Okay. We are also importing real categorical integer. As you can recall, I told you that hyperparameter space can be differentiated in real, categorical, and integer. Okay. I'm going with the same kernel. Like I'm not changing the kernel, but kernel can also be varied. Okay. So this is the parameter space I'm going with. I have alpha value. So real, that is a real number value. So it varies from this point to this point. Categorical, whether to copy X train or not. Number of restarts optimizer, that is integer, that has to be from 0 to 10. Whether to normalize feature or not, response or not, that is also categorical true or false. Optimizer, so I'm using just one optimizer. So type of the parameter space over here, that is dictionary. Okay. Now I'm using base search CV over here, as you can see. This will take into account the GP. GP is nothing but your Gaussian process model over here. Param space, that is the parameter space which you have defined. Number of iterations, for how many iterations I want to perform this optimization, and cross validation, that is five-fold cross validation has to be performed here. Okay. So now with the help of this base search fit, the X train in between Y train, the model will be exploring different options. Okay. Might take some time because we have some parameters, but when compared with grid search, it is better to use Bayesian search. Like you can compare on your own as well. Okay, so let's see what I've done last time. So last time I have some information already. Okay, so now after this, what will happen? We will get the best hyperparameters out of the base search best parameters. Okay, so the best hyperparameter you can check alpha value should be this. I can see them. So alpha value has to be this. Copy X train has to be false. Number of restart optimizer has to be 10. Normalize Y has to be true. And optimizer I'm using only one, so it is giving that one. Okay. So by utilizing these best hyperparameters, the model can be constructed further. Okay. The best model will be base search dot best estimator. Okay. Now this I have got based on this best model, what is the prediction for X train and X test. Okay. Can again make the assessment and get the scatter plot. And so like this, you can implement base search CV in Colab. Okay. So with this, I have demonstrated that how Gaussian process regressor works in the Colab, how you can utilize that. At the same time, if you want to perform hyperparameter tuning that is based on the base search CV, that also you can do. Okay. So what I want you to do is you need to explore different options. Like we was looking at different options over here, different search algorithms. I want you to look at different search algorithms in base search CV and try to implement this in your problems. Okay. Since most of you are working with the regression problem, so instead of going with the grid search, you should always go with the Bayesian search CV. It will help you in getting better parameters space for model, and the model capability will be also enhancing. So this was it for the today's class, and so I will share the content with you. You can look at the collab file and you can look at the slides as well. So I just want to know if there are any queries, just let me know so that we can answer those queries. Was it understood, first of all? Did you understand what happened, how Bayesian search optimization works exactly? Okay, I'm looking for some responses from you. Yeah, tell me. Please unmute yourself. data set for GPR. Which data set? The data set which I'm using. Okay, I'll send the data set. Anything else? Okay, so I would like to discuss about the project reviews. There were some candidates for which project reviews was not done yesterday, especially from section B. May I know the reason why they haven't joined? Group number 5. Do we have group number 5 here? Do we have group number 5? Tatakunda Puneet, Manoj Kumar, Mahadev Naidu. Please unmute yourself.
Yes, sir.
Why haven't you joined yesterday? What was the reason?
Sir, we thought we can give afternoon. We joined at 2 p.m., sir.
Joined at 2 p.m. means
We thought we can give